Welcome back. The objective of this video is to introduce semilog plots. So we're going to graph equations that have a wide range of values on a logarithmic scale. So semilog, half of it will be on a logarithmic scale, the other half will be on a normal unit scale. So we see here a semilog plot is a graph that combines a logarithmic scale for one axis and a linear scale for the other. It is used to plot data that covers a wide range of values, where a linear plot would make it difficult to see the details. The semilog plot will create a graph that reveals the details of the data while still showing the overall trend in the lesson. We will see how to create and interpret semilog plots in this video. So let's go ahead and plot a linear function. We're just going to plot y equals x on the normal Cartesian plane here, and we get those data points, and then we can draw a line through those, and there's the graph of y equals x. Now in B, we're asked to use a semi-logarithmic axis at the right. So the semi-logarithmic axis at the right, you can see how these are scaled, and the distances get smaller and smaller the closer we get to 1. And 1 here is really like 10 to the 0 power and 10 to the first power. So as our exponents get closer and closer to 1 here, we kind of squeeze our scale a little bit. It's more of a logarithmic scale than a linear scale. So we're asked to use the semi-logarithmic axis at right and plot y equals x. So when x is 1, y is 1. When x is 2, y is 2. When x is 3, y is 3. X is 4, y is 4. X is 5, y is 5. And you can see here the shape of this is changing because of the scaling of the graph. So these are in base 10. So what do we notice about the graph of the linear function? Well, that linear function, I think I missed one. Well, I missed 0, 0. But our linear function on a semilog plot appears to be, well, logarithmic. So in answer C, the linear graph appears logarithmic on the semilog plot. And in the note at the bottom, it says, mathematically, we treat a logarithmic axis as a transformation of the variables. For our course, for AP Pre-Calc, we will plot data pairs x, y in a semilog plot where we are working with the transformed data pairs, and we'll use our y values will be the log base 10 of y or the natural log of y. So our ordered pairs x log y or x natural log of y. And think about log y as a variable. The logarithmic scale is a great tool to compress a large range of data into a small space and be able to detect small variations in the values of the data points in the set. So now in example 2, we're asked to consider the function f of x equals 9 times 3 raised to the x. The table below shows the values of our y values, or f of x, at selected values of x, so our inputs and our outputs. To graph this function, we would need a very long y-axis. However, if we use a semilog plot, where the y-axis is scaled to powers of 10, we can graph many of the function's values, or get a pretty good sense of it. So we're asked to plot the points for the function below. And let's take a look at our y-axis. Our x-axis just goes from 0 to 9, but our y-axis might be hard to see, but the first group here is 10, or 10 to the first, and the next group goes to 100, or 10 to the second, and the next group goes to 1,000, 10 to the third, 10 to the fourth, and so forth. So when we plot our points, when x is 0 and y is 9, well, we can go, that's just 9 is here, just under 10 to the first. And when x is 1 y is 27, so somewhere between the 2 and the 3. That looks like about 27. And y is 281. That's going to be a little bit more squeezed. We're going to be right at 8 there. So that would be like 10 to the 1.8 kind of thing. Now that wouldn't even be that. And so forth. So we just keep plotting those points. 3 is 243. So I think that's, 100, 200, about halfway between the 2 and 3. And 729 is just over the 7 and the 8. And then 2,187, just over the 2 over 10 to the third, and so forth. So we get this data set, and that appears to be linear. So what do we notice about the graph of the exponential function on this semilog plot? An exponential function becomes linear on the semilog plot. In C, we're asked to write log base 3 of f of x in the form log base 3 of f of x equals mx plus b. So we're going to rewrite our function as a linear function. That's what we're asked to do, and find the values of our slope and our y-intercept. So we have our exponential function, f of x equals 9 times 3 to the x, and we want to rewrite it in log base 3. So we are going to log 3 both sides. So we get log 3 of f of x equals log 3 of 9 times 3 to the x. So we have multiplication here. I'm going to apply my logarithm rules and properties and expand this logarithm on the right. So after I've logged both sides, I have log base 3 of f of x equals log base 3 of 9 plus x log base 3 of 3. So simplifying my left-hand side, simplifying my right-hand side, log base 3 of 9 is 2, log base 3 of 3 is 1, and we get a function of y equals 2 plus x, or x plus 2. So that is a linear equation that's a representative of 9 times 3 to the x. And now we can put that on our coordinate plane. I have an m of 1, or slope of 1, and a b of 2, or y-intercept of 2. So I can go ahead and plot points and start at 2 and then just continue with a slope of 1, and I can graph my function. I've graphed my function. We do want to make sure we label our x's and x and y-axis. So our y-axis, right, is log base 3 of x, right? That's our y, and our x-axis is just our x values. So that wraps up our first video and the introduction to semilog plots, and gave you a nice example of how to convert an exponential into a linear equation by using our logarithms and logarithm properties. And we'll get some more practice with this when I see you in class.